We have been talking about viscosity, and please understand that viscosity is very important when we talk about the mechanical parts. Like the viscosity of oil going inside a watch and the viscosity of oil going inside an engine would be very different. It depends based on what kind of heat they have to absorb, what kind of running conditions they have, what kind of speed they have to maintain. So different sort of mechanical requirements will be having different need of viscosity. So let's look into some numerical practice of viscosity. So if I say that I won't be writing the question, I will be dictating it and will be drawing in parallel. So if I say that there is a stationary plate having velocity 0 and there is a plate on the top which is moving at a velocity of 3 meter per second. So this is moving at a rate of 3 meter per second. It is filled with a liquid of viscosity 20 poise, has a density of say 1200 kg per cubic meter. So these are the properties of fluids inside the plates. What you have been asked is that first tell me what is the shear stress on the upper plate. Fine. So this is I will write it more specifically. I want shear stress on the upper plate. Second, I want to understand what is the force required to move the upper plate if area of plate is say 5 meter square. Third, I am being asked that what is the kinematic viscosity of the system. Fine. What else can be found? We also require the distance between the plates. So consider that the distance between the plates L is equal to 4 mm. What we know that tau is equal to mu du upon dy. So over here we can see that the values available to us are not given in the standard forms. For us, mu provided is 20 poise. What we know is that 10 poise is equal to 1 Newton per meter square. Hence I can write that mu has a value of 20 divided by 10, which is equal to 2 Newton per meter square. Right? Let's move forward. I've got the value of mu. What is the change in velocity? I'm being asked du. So change in velocity is with respect to the plate, stationary plate. So the velocity at the plate which we are considering is 3 meter per second, right? So I'm being asked that what is the velocity at the upper plate. So the plate at which the velocity is desired is 3 meter per second minus the plate at which we are considering stationary is 0. So the value of du is 3 meter per second and the distance between plate dy is equal to 4 mm. So I have to convert it into meters. So 4 into 10 raised to the power minus 3 meter. From all these values, I can find that tau is equal to mu du upon dy. Mu has a value of 2, du has a value of 3 and dy has a value of 4 into 10 raised to the power minus 3. So tau will come out to be 1.5 into 10 raised to the power 3 Newton per meter square. So this is the shear stress on the upper plate. Let's flip the question. Let's have some modifications. What if I am being asked that what is the shear stress on the down plate? Similarly, you know that the mu will remain the constant because it's a property of fluid. So this will remain the constant. The space between the plates is also constant. So what would change over here? So let's see. We want that du is the plate which is considered minus from the plate which is being measured to the plate from which it is being measured is having a velocity of 3 meter per second. So du will be having a value of minus 3 meter per second. Now, if you want to talk about the distance is actually measured from over here. If you look that the distance was measured from stationary plate to the moving plate. Now we want the shear stress of the stationary plate. So the distance will be measured from moving plate to the stationary plate. If this direction is considered as positive, so this u is moving in the negative direction. This will be minus 4 mm. So this will be minus 4 into 10 raised to the power minus 3 meter. So if you solve it again, you will see that minus will cancel out and the shear stress at the down plate will again be 1.5 into 10 raised to the power minus 10 raised to the power plus 3 Newton per meter square. Fine. This part is done. So the shear stress on the upper plate is 1.5 into 10 raised to the power 3 Newton per meter square. Let's move forward. I have been asked that what is the force on the upper plate. So force on the upper plate, how do we find a force? Force is stress into area. So stress is 1.5 Newton per meter square. And what is the area provided to us? It is 5 meter square. So the area is 5 meter square. So this comes out to be 7.5. Oh, I'm sorry, I missed something. So shear stress is 1.5 into 10 raised to power 3 Newton per meter square, and the area is 5. So this comes out to be 7.5 into 10 raised to power 3 Newton. I can write this. The force required is 7.5 kilonewton. So what would be the statement for this? It would state that the force required to move the upper plate at a velocity of 3 meter per second when the lower plate is fixed at a distance of 4 mm and the fluid between the plates is 20 poise is 7.5 kilonewton, right? So we have upward force. This is 7.5 kilonewton. Now you have been asked the dynamic viscosity. Dynamic viscosity is mu by rho. Mu is 2 Newton per mm square and the viscosity is 1200. So this will be 1.67 into 10 raised to power minus 3 meter square per second. So that's the value. I can write it at the top. So this is 1.67 into 10 raised to power minus 3. Right? Next numerical, a bit complicated one in the next lecture.